Geometric dimensioning and tolerancing, or GD&T, is the language of modern engineering. Within this language, position tolerance is a powerful tool, yet its composite form is often misunderstood. Many see the stacked feature control frame and shy away, missing out on its benefits. Composite tolerancing isn't as complex as it seems. It's a smart solution for a common problem. It lets you control both the location of a group of features and their relationship to each other, all in one specification. Think of it as setting two rules, one for the group's position, another for how the features relate within that group. This dual control helps parts fit together perfectly, while allowing manufacturing flexibility where it doesn't matter. We'll break down composite position tolerancing step by step, starting from the basics. By the end, you'll see the stacked frame as an elegant, efficient tool, not something to fear. It's a must-have for every serious engineer and designer. This guide will show you what each part of the composite control means, how it affects your part, and why it's often the best choice. We'll use practical examples and comparisons to highlight its unique advantages. My goal: to demystify composite position tolerancing and give you the confidence to use it in your own designs. Let's get started. Before tackling composite tolerancing, let's review basic position tolerance. Position tolerance defines a zone where a feature's axis or center plane can vary from its true, theoretically exact position. This true position is set by basic dimensions, those box numbers on a drawing. The position tolerance creates a boundary around this perfect spot. The actual feature must fall within it. For a hole, this means its axis must stay inside a cylindrical zone, often specified as a diameter in the feature control frame. This cylindrical zone allows more variation than traditional plus-minus tolerancing, making assembly more realistic and forgiving. Position tolerance ensures features are located correctly to function and assemble as intended. It's about location, not size. That's controlled separately. The control is always referenced to datums, which anchor the part in space. With this foundation, we're ready to see how composite tolerancing builds on this idea. Let's move on. Now, let's look at composite position tolerance. You'll spot it by its stacked feature control frame. One position symbol, two or more horizontal segments. Each segment sets a tolerance and datums, representing two levels of control applied at once. The top segment, called the Pattern Locating Tolerance Zone Framework, PLTZF, controls the location of the entire pattern relative to the main datums. The bottom segment, the Feature Relating Tolerance Zone Framework, FRTZF, controls how features relate to each other within the pattern, usually with a tighter tolerance. The top segment answers, where is the group of holes on the part? The bottom, how precisely are the holes spaced relative to each other? The pattern can shift as a group within the larger tolerance, but the features must stay tightly grouped within the smaller tolerance. This dual control ensures both correct assembly and manufacturing flexibility. It's not two separate tolerances, it's one smart, two-part requirement. That's the power of composite tolerancing. To understand composite tolerancing, let's visualize it. Imagine a pattern of 4 holes. The top segment defines 4 large cylindrical zones, say diameter 1.0 mm, locked together in a perfect pattern, located by datums A, B, and C. As a group, these zones can shift and rotate within the limits set by the datums. The bottom segment adds 4 smaller zones, say diameter 0.4 mm, also locked together, but only oriented by datum A. This smaller pattern can float within the larger zones, but must stay inside them. The axis of each hole must pass through both zones at once. Think of the large zones as a corral for the pattern, and the small zones as pens for each hole, tied together but moving as a unit inside the corral. The large tolerance ensures the pattern lines up for assembly. The small tolerance ensures the holes are spaced correctly so all bolts fit. This two-level check guarantees both the pattern's location and its internal integrity. That's why composite tolerancing is so effective. It's a simple, visual way to control both the group and the details. Let's see how this solves real-world problems. Why use composite tolerance? It's all about function and cost. In assemblies, the critical need is often for a pattern of features to line up with a matching pattern, like bolt holes on a gearbox cover and housing. The exact location of the hole pattern isn't always critical, but the spacing between holes is. Composite tolerancing addresses this. The top segment allows generous variation for the pattern's location, reducing machining time and cost. The bottom segment keeps the holes tightly spaced, ensuring all bolts fit. Without composite control, you'd need a single, tight tolerance for everything, overkill and expensive. Composite tolerancing loosens the tolerance where possible and tightens it only where necessary. The result parts that assemble easily with less cost and hassle. It's a smarter, more economical approach. That's why it's the best choice for many designs. Let's see a concrete example. Picture a rectangular plate with 4 holes, each 10 millimeters in diameter, arranged in a square. Datums: A, bottom; B, left edge; C, back edge. The designer applies a composite position tolerance top segment, diameter 1.2, A, B, C. Bottom segment, diameter 0.5, A. The top segment, PLTZF, creates 4 large tolerance zones, each 1.2 millimeters in diameter, located by the basic dimensions and datums A, B, C. The pattern can shift or rotate as a group, but the holes stay locked together. The bottom segment, FRTZF, creates 4 smaller zones, 0.5 millimeters in diameter, only oriented by datum A. This pattern of small zones can float within the larger ones. For acceptance, each hole's axis must be inside both its large and small zone. The manufacturer gets a generous 1.2 millimeter tolerance for the pattern's location, but must drill the holes precisely relative to each other within 0.5 millimeter. This balances ease of manufacturing with assembly reliability. The result, parts that fit together without unnecessary cost. Composite tolerancing makes this possible. It's practical, efficient, and clear. That's how you apply it. Don't confuse composite position tolerance with 2 separate single-segment tolerances. They may look similar, but they're fundamentally different. Composite tolerance, one symbol, stacked segments, means a single requirement with 2 parts. 2 single-segment tolerances are independent. The pattern could satisfy one and not the other. With composite control, the tighter pattern must exist inside the looser one, matching real assembly needs. Using 2 separate tolerances allows the pattern to float freely, which isn't usually the intent. Composite tolerancing links the requirements, ensuring the pattern's internal precision and correct location as a group. Always use composite control when you need both pattern location and internal feature relationship. It's the only way to guarantee both. This distinction is crucial for correct design and inspection. Remember, composite for linked control, separate for independent requirements. Inspecting composite position tolerance is straightforward with the right tools. Most use a coordinate measuring machine, CMM, which handles GD&T and composite controls. First, establish the datum reference frame, ABC, and measure the features. The CMM checks the pattern's location against the top segment, PLTZF, then checks the internal spacing against the bottom segment, FRTZF, usually by reorienting to just datum A. Both checks must pass. Without a CMM, a functional gauge can simulate the mating part and check both pattern location and feature-to-feature spacing. CMMs provide detailed data, but gauges offer a simple pass-fail. Use the method that fits your needs and resources. Composite position tolerancing isn't obscure or overly complex. It's a logical, efficient tool. It separates control of a pattern's location from the relationships within that pattern. This lets you design parts that are both functional and economical. A larger tolerance for pattern location gives manufacturers flexibility and reduces costs. A tighter tolerance for feature-to-feature spacing ensures assembly and interchangeability. Mastering composite tolerancing makes you a more effective designer. Start with simple patterns, discuss with your team, and build confidence. Embrace composite tolerancing to create better, more reliable products.